Well, good afternoon, agents and naturalists and gardeners and other interested people. Today we'll have an advanced webinar on physical weathering, and this is January 14th, 2015. I'm Dr. John Galbraith. I'm a soil information specialist with Virginia Tech in Blacksburg, and I'd like to welcome you to the advanced webinar series. Well, there are two types of weathering, and it's physical weathering and chemical weathering. And the catchphrase I use for physical weathering is disintegration. And the catchphrase for chemical weathering is decomposition. Today we will only talk about physical weathering. And that's essentially when bedrock fragments are spread apart, weathering rinds develop, and loose particles are removed. And we can see in the picture the disintegration of this wedge of bedrock. You can see the macropores or cracks that have developed. In this area is where water, ice, salts, and other materials, roots, can enter in between the rocks and then push them even further apart. In this particular photograph, the rocks are very tightly held together. So we need to have some kind of force in place to move some of these looser rocks out of the way so that the rest of the physical weathering can take place. Physical weathering precedes chemical weathering, which then takes place on the edges. So the main factor of physical weathering is to expose edges to chemical weathering. And you can see where some of that is taking place right now by this iron oxide coating that's forming in between the rock fragments. Well, physical weathering is a series of processes that act upon parent materials. And the parent material, again, is the bedrock, sediment, soil, or organic matter from which new soil forms. And physical weathering acts on rocks and large crystals and cemented sediment. If there is any cemented sediment held together by, these are where sand, silt, and clay particles are held together by secondary minerals, then those also are the subject of physical weathering. The main result of physical weathering is to decrease the grain size, which increases the surface area exposed to chemical weathering, heat, and energy. And so again, as the grain size decreases from boulders to cobbles to gravel to sand and further into clay and oxides, then the surface area increases greatly. The physical forces that act on the parent material continue to act until an equilibrium is reached with the energy and the forces around them, the heat and the energy. But as soon as any part of that equilibrium changes or is disrupted, then physical weathering adjusts accordingly. Now here in this example, you can see the physical weathering. This is being conducted by humans, where they physically are moving rock particles into a different location, and that's what physical weathering does. It breaks rocks apart or it moves them to a different location. Now, one thing that's interesting in this picture is the amount of rock that's been removed from this coal seam area. And if you think about all of the weight of rock that was pressing down on this rock in the bottom of the pit, all of that weight has been removed. And so we have a reactionary process taking place. And this is the list of processes that make up physical weathering. We have separation processes where individual rock fragments are separated from the main bedrock deposit. And that can be unloading. Another term for that is exfoliation. frost pull, plucking up by tree roots, crystal formation, crystallization, woody root expansion in between rocks. All of these can separate rocks. We have abrasion processes and fracturing processes. And fracturing can be part of rockfall. It can be from impact with meteors or atomic bombs and volcanic explosions. Well, our physical weathering, we start with unloading. That is the one that is the dominant process of all. And again, like in the example where we showed the coal pit, and I showed you where maybe 100 feet of overlying rock was removed, it released a tremendous amount of overbearing pressure. And when you remove that pressure, then the rock underneath expands. And as it expands, it separates along the original deposition layering. It can also separate between crystals. It does not, however, crack between in the middle of crystals. It cracks between crystals. All right, and then the expansion that takes place after the release of the pressure is the precursor to all other physical, and I could add chemical weathering. And in almost massive rocks that did not have much layering to begin with, like the granite, then we get a rind that develops and peels off, and this is called spalling. And this rind develops parallel to the surface. And again, it's just a release of pressure, allows cracks to develop, and then eventually these slabs fall off or move off. And this is similar. The reason it's called exfoliation is very similar to your skin. It loses cells constantly, so you can imagine these like being cells coming off of the skin of the granite underneath. Well, sedimentary rocks are deposited in layers and often parallel to the surface. They may end up being tilted later, but typically they start out being parallel, and they tend to be flat or parallel to each other, as well as parallel to the surface. But when the pressure above them is decreased, they easily separate back between those original deposition layers. Now, some cemented rocks may have fewer horizontal layers or planes that separate the deposits, and they may be more massive. Limestone, especially limestone that formed from coral reefs, tends to be very massive. Sandstone and shale tend to be very thin bedded. Sandstone would be thicker than shale, but not as thick as limestone. Well, they undergo pressure changes as they come closer to the surface and to develop vertical cracks. Metamorphic rocks may recrystallize in thin layers, and that's how they end up with thin layering to begin with. And igneous rocks cool slowly, may form larger crystals or separate into larger fragments. They may not have that thin layering, and so often igneous rocks will form mountains once they have weathered. All right, here's a picture of the thin layering left over from sedimentary deposits. You can see that on the upper left and the upper right. The material on the upper right is part of what's called the Badlands complex. And that area was, again, very young geologically and never deeply buried, very similar to our coastal plain. We don't have an example of this in Virginia, but the layering we do have examples of, and it does resemble the coastal plain deposits. Well, here's some gneiss. The white color is going to be primarily quartz, and the darker minerals are going to be amphiboles and biotite and other primary minerals that begin to weather. But again, you see the thin layering that forms as these rocks recrystallize. Here's a picture of igneous rock, and you can see it's much more massive. There are certainly cracks in it, but they're not as thinly bedded as the gneiss or the sedimentary rock. And here you can see basalt, which is another igneous rock, and you can see the columnar structure that forms. Very interesting type of rock. This kind of rock in Virginia weathers into shrink swell clays. The granite, however, does not typically weather into shrink swell clays. There are some igneous rocks that do weather into shrink swell clays. That would be gabbro. All right, well, unloading, that's number one, and that process explains most of the physical weathering in Virginia. However, there are some other minor types of physical weathering. Let's expand our view to go beyond Virginia and talk about the entire North American continent. We can have fire or extremes in temperature, and if there is confined water or air, if that expands rapidly enough when exposed to either fire or extreme cold, it might widen existing cracks between layers of rock or between individual crystals within the rock. But the cracks have to exist already, and those cracks develop as unloading proceeds. Now, if water or air is trapped in open cracks, open to the atmosphere, it'll just simply expand and just come right out of the rock and form ice on the side of the rock. It has to be confined, or else it can't exert its pressure, and the pressure happens when either the air expands or the ice expands as it freezes. Rocks in desert regions, however, may freeze at night and then heat up rapidly in the sun the next morning. And when you get the different rates of expansion and contraction, part of the rock may still be contracted, part of the rock may be hot and try to expand, and therefore you can develop, or I guess you can widen the existing cracks that way. And this would be very similar to exfoliation. In fact, some people consider this a type of exfoliation because the rock would tend to peel on the outer edges. All right, on another type of way where we can take individual rock fragments and pull them off of a solid piece of bedrock, again, only along cracks that already existed, is to use freezing. And there's two different ways that this can happen. If the soil is freezing from the bottom up, and this would not be happening in Virginia, but it might happen above permafrost at high latitudes like Alaska, then sometimes the soil is unfrozen at the top and frozen below. And the permafrost is -4 degrees Celsius, and so that's quite cold. And so it will try to refreeze the soil that melted the previous summer and refreeze it during the fall of the year. And if that's the case, if there is water between the bedrock layers, that top layer of bedrock may be subject to ice growing underneath it. Well, that ice has to expand, and it is confined by the soil that's on top of the rock. And so as the ice grows, it pushes those rocks up into the loose soil that's not frozen. Then eventually the soil becomes frozen, both from the bottom and from the top, and eventually all of the soil is frozen. But before it becomes frozen, some of that soil may fall underneath the rock that has been pushed up by the ice. The ice melts, soil may slip underneath that rock before it can settle back down into its original position. And if that happens, then it is effectively separated from the bedrock underneath it. Again, the ice didn't crack anything. All it did was push rocks apart in places where cracks already existed. Now, the opposite can also happen. If bedrock is near the surface and the surface is frozen solid, but the but the subsoil is frozen, and this can happen in Virginia. Then ice may form around the top of the rock fragment and I guess grab it or hold on to it. As ice forms deeper and deeper into the soil, it expands toward the surface because layers of moisture keep freezing, and so it would get higher. In other words, the land surface would actually be raised. And we've all seen that. It's called frost heaving. And if the rock that was attached to the bedrock underneath is frozen to the ice that gets heaved toward the surface by expansion, then it will pull that rock away from the bedrock. And again, as ice begins to melt, if sediment slips in underneath that rock, then it can no longer resume its original position. And there's a book by Schaetzl and Anderson. It's now in its second edition. It's called Soil Genesis and Geomorphology. And it's my favorite textbook. And it explains these processes of soil grabbing, frozen soil grabbing onto the top of a rock, the rock being lifted, and then sediment settling in underneath the rock. And this is a picture of some of those rocks that have been plucked from the granite bedrock underneath them. It's quite impressive. I would hate to have been there when all of this happened. Okay. Well, how do we separate, once we separate rocks along layers and between crystals, then how do we move them out of the way? Well, one way is wind and water action. In this case, here we have water and wave action that would clean off the loose particles and crystals that had come apart in the process of physical weathering. So they don't actually break rocks, but they do move the loose rocks out of the way. Again, this picture shows the layering that already exists between the rocks, and these are the original deposition layering. And here you can see the pattern. This would be a windblown deposit. This would be an old sand dune that is now turned into sandstone. And here's some thin layering of bedrock. And you can see that weathering, once these cracks develop, then chemical weathering can start to take place and gaps occur, and then loose fragments occur, and they can be pushed apart. I have time for a few questions. If anybody has any, please use the chat box. All right, today we don't have any questions, so we'll proceed. But if you have any, please use the chat box during the talk, and we'll discuss. All right, here's another instance where rocks that were already separated now have tree roots growing between them. And looking at this tree, I would say it's not going to be long before this tree topples over. And when it does, it's simply going to lift the rocks away from their bedrock component. So this would be solid bedrock toward the bottom. And these rocks were separated by tree roots growing in it. The roots did not crack the rocks apart. All they did was exploited a crack that already existed between the rocks. But when the tree falls, the tree roots will hold on to these rocks and pull them away, and this is called plucking. Here's an example of crystallization, and we know that this is salt water, and so in that salt water would be crystals. And so this crack would have been an existing crack in this igneous rock. But because it's right next to the ocean, the sea spray and the wave action would have allowed salt water to get into this crack. And as salt crystals grow, they exert a tremendously high force. Again, that water has to be confined to some extent. And so when this was a very, very narrow crack, it would have been largely confined. the same thing with these cracks in the rock that's shown in the desert. Salts blow up out of the desert basins, land on the rocks, get a little bit of moisture, move down into the existing cracks, and then simply spread. The growth of the crystals pushes the rock apart along cracks that already exist. Same in both pictures. It's just one is in the desert, one is near the ocean. Well, here we can see where roots have expanded, and you say, well, you see this root, this tree has actually cracked this rock. Not really. The root would have simply expanded within a crack that already existed and pushed these two fragments further apart. Same thing here where this tree grew between these fragments that used to be attached. You can match up this layer with this layer on the rock. Well, now it's been pushed sideways by the expansion of this tree. Not cracked, but simply spread apart. Well, here's a different process. We've simply been talking about processes where physical weathering widened existing cracks. Now we're going to talk about how physical weathering can remove particles. Now we showed one example where wave action cleaned off loose crystals, but here's another action, and it's called abrasion. So minerals on the outside edges, and this is where that surface area and edge relationship comes in. So as the surface area decreases because of unloading and expansion and cracking, then the surface area increases, and that leaves more area to be attacked for chemical weathering. And what happens then is we develop a weathering rind, and this is an area of more highly weathered rock around the outside of an unweathered rock. And so if we break that weathered material off, then we get it. It gets broken off in the process called abrasion. And so as rock fragments travel or are transported by ice or water or wind, then abrasion between the rocks breaks off the weathered loose material. Again, it's chemically weathered, and so it is looser, and it does get broken off by the collision between rocks. So the farther rocks move, the more times they collide with each other, and the more of the weathering rinds get broken off. That's why when you go down into rivers, you pick up rocks, and they are very hard all the way to the edge. And that's because the weathering rinds have been knocked off, and the solid core remains. But if you go into the soil in the river terraces, you can find rocks that are very old and have a weathering rind in place. And that knocking off of the edge is why big rivers have mostly rounded rocks, whereas headwaters have mainly sharp rocks. Well, here's a picture of the weathering rind. This is where chemical weathering has taken place. But look, the more sharp the edge, the thicker the rind. It's not as thick on the flat surface, but it is thickest on the very edges. Well, this is what collides with other rock fragments, and after the collisions, you can see most of the weathering rind has been knocked off, as in the upper center picture. Again, here you can see where the rind is thickest on the edges. And here's some rocks where part of the weathering rind has broken completely free, and you can see the hard center core. And of course, if that continues, you end up with a polished core with no weathering rind. And once that gets back out of the river and into a soil, then a new weathering rind begins to form. Weathering rinds don't form typically in the air. They typically form in the soil, where they can undergo chemical weathering. Well, here's abrasion in water, and you can see how rounded these sand grains are. And also this pebble. You can see how nice and rounded and polished it is. There is no weathering rind left. It continuously got knocked off, and now we have a solid rock in the middle. Here again, the majority of rocks are weathered. Even this flattened rock, which would have started out like a very thin layer, like a sedimentary rock, and you can see how the edges have become very well rounded. The skipping stone, I call those. Well, we also get abrasion by windblown sand, and you can see the coarse sand here in the desert, and you can see how the sand that is blown by the wind, the coarser sand can't get very high, but that would be the sand that would do the most abrasion, and so the bottom of this rock is now very thin, and eventually it will fall over. But the sand grains that get higher up in the air are not as large, and so they don't have the abrasive power, and that's why the top of this rock is not as eroded. Plus the sand, it takes more energy to raise the sand higher, and it takes less energy to raise it just a very short distance. Well, here you can see how this rock is polished on one side and pretty rough on this side. And that's because this is the prevailing wind direction. The sand keeps striking this side of the rock. You can even see where the wind has caused the sand to be scoured out around the bottom of the rock, just like moving water would scour sand in a river bottom. But anyway, this side of the sand of the rock that's exposed to the blowing sand is polished. And this is called a Ventifact, and vent would be wind. So it's like an artifact, but it's a wind polished rock. And here's another wind polished rock, and you can see how nice and shiny the edge is, even though I know that this is a high silica rock because of the fracturing pattern here on the edge. Well, fracturing. This is when a crack develops through the center of a crystal or a solid piece of rock. And one way that that can happen is by freefall. And so if rocks fall off of an exposed cliff like this, and if they land on top of other rocks that have some surface underneath them so that the rock gets trapped between two hard surfaces, the falling rock and a hard surface, then it can actually break in half. Now typically, though, I've found that when you go up to a pile of rock like this and you say, oh, the force of gravity has caused this rock to split in half, most of the time, if you look closely along these edges, you'll see that it actually had already split in half while it was still up on the cliff. And there are secondary minerals deposited in the layers between. And so really, even this type of catastrophic energy simply separates rocks along surfaces where they were already separate. Now, this particular rock looks pretty fresh, so this one may have broken in half, but most of the rest of these have an iron coating on the edges, and so probably were already separate before they fell. Well, here's a quiz. Fire, salts, root, and ice are likely to A, split rock crystals in half, or B, push them apart along existing macropores, layers, cracks. And the answer would be B, and that means push them apart along existing cracks. All right, our next advanced webinar will take place in February, and you can check out the Virginia Cooperative Extension website for recordings. They will be posted soon. I've also connected you with a survey if you would like to share your input on webinar content. And then I will share webinar announcement with you and other agents, other naturalists, and other gardeners. If you would like, just let me know by email. Let's go back to fracturing, because I did want to cover just very briefly the idea that meteor impact can actually fracture sand grains, and that is one of the pieces of evidence that a meteor has struck. Now, it doesn't happen very often, doesn't happen very widespread, but over the course of the history of the world, it is quite extensive. Another cause of fracturing could be the intense heat and pressure caused by an atomic explosion. However, the fracturing would take place only right in the exactly where the bomb explodes. And I think some of that evidence has been found in the areas where the nuclear testing was done, when it was done above ground and below the ground. There is some evidence of fracturing. But again, it's not something, nuclear, thank goodness, nuclear weapon explosion is not very widespread, never was. But on the islands where these were tested, I'm sure you can find some fractured crystals. Again, a minor component compared with abrasion and unloading. Well, again, I'd like to thank you for being here today, and I hope you have a good day and look forward to seeing you at the next advanced webinar series.